Hello once again, YouTube. We're back with another example. This one we'll call it number example 9. So what is the first question that it's asking? It is, what is the clock cycle time in a pipelined and non-pipelined processor? So for the pipelined processor, it's simply going to be 350. Why? Because in 350 picoseconds, we are able to allow enough time for each of the other stages, which are all less than 350 picoseconds. Okay? Essentially, if we recall that we have, how I like to imagine this is that in a pipelined version, we can have all 5 stages, slightly longer than each other. Okay, and because of this, the pipelined version, no matter if we have, so this one is the instruction decode, which is the longest, and that's why it's also the largest. We can fit each one of these other boxes within the same region, okay? And because of that, we are allowing for the other computation to take place, or we're allowing enough time for the other computation to take place. Like if we take this, we'll call this one the instruction fetch. Okay, if we take it and this length is 350 picoseconds, so then we're allowing enough time for this computation to happen. Okay, so because of that, each clock cycle has to be 350 picoseconds, allowing for the computation to happen. Okay, so 350 picoseconds for a pipeline, I don't know how to spell, pipeline processor. I am pretty sure I spelled that wrong. It's oh, it's right here, my goodness. It's literally right here. So it's processor. Good thing I'm not being evaluated on my spelling. Now, for a non-pipeline processor, okay, we have to allow time, one clock cycle, to be the entirety or the sum of everything, right? Because in one clock cycle, we have to allow time for everything to happen. And because of that, we're going to have 250 plus 350 plus 150 plus 300 plus 200, which is 1250 picoseconds. Now, part B, it asks, what is the total latency of a load word instruction in a pipelined and non-pipelined processor? Okay, so for a pipelined processor, we have to have all 5 stages, and all 5 stages theoretically take 350 picoseconds. Why? Because if it's pipelined, using that box example as before, we're going to have to be able to fit one of those smaller boxes inside that big box, right? Because we're going to have instruction. So we're going to have instruction fetch, instruction decode, execute, memory, and write back. And then in a pipeline, we would go on to the next instruction, which would be instruction fetch, instruction decode, execute, memory, and write back. Okay, so because of this, we have to allow enough time for the other instruction or the other blocks. We have to allow enough time for the other blocks to happen within, even though they're shorter, they have to happen within the same amount of time. So for example, this one's 350. This one is 350. This one is also 350. Right back, we have to allow 350 just in case. And this one is also 350. Okay, and because of that, it's just going to be 350 times 5, So we can type that on the calculator. 350 times 5 is 1750 for load word in pipeline processor. Next, once again, if we are just having a single line of code and it's load word, it's again only going to take 1250 picoseconds in the non-pipeline version. Why? Because it's only a single line of code, so we can take each of the individual times as is. So it's going to be the sum of each time, and it's going to be 1250 picoseconds. Okay, if we can split one stage of the pipeline data path into two stages, each with half the latency of the original stage, which stage would you split? And what is the new clock cycle time of the processor? So we would take the longest time, because if we split it up, we're going to get 175 each, okay, which is a lot shorter than 350 picoseconds, okay, which essentially it takes that and breaks it down into two stages. Great. But now we're going to have a new clock cycle for a pipeline processor. Why? Because it's always the longest stage, or the longest allocated time to a stage. That is our clock time. Why? Because once again, we have to allow enough time for the other stages for its computation to happen within the pipeline. So because of that, we're going to take the 350 and we'll split that. And our new clock will be 300 picoseconds. Great. Assuming there are no stalls or hazard, what is the utilization of the data memory? So what does the data memory use? It's going to use the load and store. So because it uses load and store, okay, so this was A, this was B, this was C, now we're on D. Because it uses load and store, it's going to be 20% plus 15%, which gives us 35%. And E. Why is it E? Well, I mean, by deduction, you can just conclude that, well, first let's read it. Assuming there are no stalls or hazard, what is the utilization of write register port or the register's unit? So what does it use? It uses assuming, what does the write register port or the register's unit? So if we scroll up, this is the register unit. And what does it do? Or what does it use? It uses write data, and it uses what does it use? What is the utilization of write register port of the register's unit? So this is the write, and what does it utilize? Well, it utilizes ALU logic, right? So it uses this and this, because when you write by stuff from this mux, okay, so I'm thinking out loud here, but here we go, hear me out. So this mux gets information from the read data from the data memory and or the ALU, which is then written back to this register. So because of that, we are dependent on the load data or the ALU logic. So that's going to be 45% plus the loaded data, which is going to be 15%, which then implies that it's going to be 45. Oh no, it's going to be 20 here. It's going to be 65%. So that concludes that.